Now, we will discuss about the diffusion of liquids. So, you see that Na in 1D, we can write that Na equal to this Ca by C Na plus Nb minus Dab into C dxa dz, where Xa is the mole fraction. Now, this automatically is the mole fraction Na plus Nb. Now, this concentration term we can get rid of, the bulk concentration, we can replace it by rho by m average, right. So, density is in kg per meter cube, where or in gram per meter cube, and here m will be in gram per gram mole. So, obviously, it gives you gram mole per meter cube, which is C. So, it is rho by m average into dxa dz. So, naturally, for diffusion of A through non-diffusing B, we can write this Na. See, Na for gas, what was the expression? Dab into P RTL, then delta of Pa by ppm average, right. So, here for liquid, we can write it as Dab, RT will not be there, by L, then P is equivalent to concentration. So, rho by m average into Xa0 minus Xal by this XBm average. So, here this Bm is the mole fraction, right. So, basically from why it happens? Basically delta Pa, if we write it in terms of gas mole fraction, what it will be? Dab into P by RTL into P into delta Ya mole fraction and P into Ybm, right. Because in the log mean, in the numerator we have pressure dimension. So, that pressure we take it out. So, these two cancels out, right. So, now in case of liquid, if I just try to map it without deriving it, so this RT will be absent, P can be replaced by concentration, and this is the liquid mole fraction difference between the 2 points, and Y bar Bm can be replaced by X bar Bm, right. And second is diffusion of or equimolar counter diffusion, equimolar counter diffusion of A and B. For gas, it was Na equal to Dab by RTL into delta Pa. So, for liquid, it will be simply Dab by L into rho by m average into Xa naught minus Xal, correct. So, that is the expression for these liquid molar fluxes. Now, immediate question arises next, how this Dab can be measured. Just like in case of gas, we have discussed the twin bulb and the Stephen tubes method. In case of liquid, how it can be measured. So, This we can do in something called diaphragm cell. Measurement of liquid phase diffusivity. What do? We have a cell which is partitioned into two halves by a diaphragm, right. It is a glassy diaphragm through which we have the pores, and the liquid can diffuse from one compartment to other, and here inside the pores we will have no convective transport. So, here we put the starter in order to homogenize the concentration in the two compartments, and let us say this thickness of the diaphragm is L and area of the diaphragm is A, right. And here the concentration is Ca1, here the concentration is Ca2, the volume is V1, the volume is V2 here. So, first is the molar transportation rate. How we can write that? So, it is Na, see it is a kind of this equimolar diffusion, right. Yeah, we can write this as equimolar diffusion from one compartment to another compartment. Basically, if I have this a concentrated solution, concentrated aqueous solution in compartment 1 and pure water in compartment 2, so let us say it is an aqueous solution. So, that component will diffuse through this diaphragm from 1 to 2, whereas water will diffuse in the opposite direction, right. So, it is an equimolar counter diffusion. So, mass transportation rate, apparently it seems that Na into A, but if we look into the diaphragm, see it has got certain pore openings, it is not the entire area. Now, the diaphragm has got a volume wise void fraction epsilon. We assume that this is same as surface void fraction, or alternatively we can evaluate this surface volume fraction, though it is not so easy. So, anyway, let us say we know that. So, the diffusion actually taking place is not through the area of small a, but rather A into epsilon, right. And the flux Na, it's we can write incorporating the concentration as dAb into L into Ca1 minus Ca2, right. Now, again the same mass balance, minus of V1 dCa1 dt equal to this. Now, L, regarding L, see L is the actual path or actual thickness of the diaphragm. However, a pore may be like this, right, a pore may be like this. So, its path length is much higher than the thickness of the diaphragm. So, here we have the pore length, if it is L prime, then L prime by L average, right, the average of this quantity is called the average tortuosity, represented by tau, right. So, actually it is not L, but the L prime, and L prime is L into tau, where tau is the average tortuosity of the diaphragm. So, we have dAb into A into epsilon divided by L into tau into Ca1 minus Ca2, and similarly plus V2 dCa2 dt, the same dAb into A into epsilon L into tau Ca1 minus Ca2. Now, we will simply cross multiply V1 here and V2 here, and next we will add. So, d dt of Ca1 minus Ca2 equal to dAb A into epsilon L into tau 1 by V1 plus 1 by V2 Ca1 minus Ca2. So, that becomes my governing equation. So, you can integrate it at t equal to 0, Ca1 equal to Ca0, then Ca2 equal to 0 maybe, and at t it is Ca1 and Ca2. So, if you integrate, you will get an equation, integrated form, and upon measuring the concentration after some time allowing for diffusion, right, we can calculate the DAB provided we have an accurate estimate of epsilon and tau, the porosity and tortuosity. So, that is the measure of liquid diffusivity. Now, regarding the predictive equation, we have this Wilke-Chang equation, right, though it is much older and there are a lot of modifications has been proposed over times, but it is simple, but however it is less accurate. So, what is that equation? And note that DAB liquid, it varies in the order of 0.5 into 10 to the power minus 9 to 2 into 10 to the power minus 9 meter square per second. So, it is in the order of 10 to the power minus 9 meter square per second, contrary to the gas phase diffusion, which is 10 to the power minus 4 to 10 to the power minus 5. So, what is Wilke-Chang predictive equation? Of liquid diffusivity? It states that DAB 0 equal to 1.173 into 10 to the power minus 16 phi into MB, phi is called the association factor, to the power half into T divided by VA to the power 0.6 into mu, right, and 0 refers to the infinite dilution. So, it is actually not valid everywhere, it requires this infinite the diluted solution of A in B, right. But still it is the simple working form we have, at least in undergrad we can use this equation to get this diffusivity value. So, what is important to note that we do not have to remember the coefficient, it is T divided by mu, right. Mu is also dependent on this temperature. So, for liquid again there is empiricity, right. The mu we have discussed it in fluid mechanics, it can be represented by some exponential Arrhenius type relation. So, it is not very well documented or standardized, right, or coming up from certain this theory. So, it requires certain empiricity to estimate or to express mu as a function of temperature. So, anyway, tentatively we can assume that dAb naught is proportional to T divided by mu, and if I know this mu functionality, it can be expressed or it can be measured. So, that is because the liquid diffusivity, you see it is difficult because the liquid phase itself is a phase which we less understand. Like gas phase, we have a model gas equation, that is ideal gas, and from there we can well document the deviation of this real gas behavior from that of ideal gas, as we have discussed in thermodynamics. But in liquid, there is no, in classical domain, there is no ideal liquid model, right. It comes in statistical thermodynamics, but again there are debates. There is something called Ising model, which is in statistical thermodynamics, which describes something like ideal liquid, right. but that is beyond the purview of classical thermodynamics and we are not going to discuss this here. But still liquid is highly non-ideal, and that is why, because we cannot say that there is no interaction between the liquid molecules as the intermolecular spacing is too small compared to the gases. So, what we have here, that we have to get ourselves satisfied with that empirical this equation of Wilke-Chang. There are a lot of modifications, but they will not give you a simple form like this. Anyway, next we will discuss about the diffusion through variable area, and it is a very common specifically in polar geometry, right. Think of a naphthalene ball is diffusing, right. Naphthalene ball, from the naphthalene ball which is spherical in shape, the naphthalene is diffusing, it is sublimating into here, right. So, here what will happen? If I have a naphthalene ball of radius RS, and if I think of a shell between R and R plus dr, it is a case of, first we have to understand, it is a case of diffusion of A through non-diffusing B, right. B is here, A is naphthalene. So, what you can write, Na into 4 pi r square is equal to small na, here small na represents the molar flow rate, not the flux, right. Now, you see this Na, how we can write here, we will again go back to the basics, Na equal to Pa divided by P, Na plus Nb minus Dab by Rt dPa dr, right, and Nb equal to 0. So, Na into 1 minus Pa by P into minus of Dab by Rt into dPa dr, that is equal to this, sorry, it is equal to minus of Dab by Rt into dPa dr. So, Na we can get as minus of Dab into P. We cannot use the integrated form because the R is continuously changing. So, that is P minus Pa into this dPa dr, and that directly we have to substitute back. You may be thinking that we can think that okay, we will first integrate this equation between R equal to Rs and R infinity, but here we have a variable R. So, in this derivative form we have to substitute this Na and then we have to integrate. Okay. So, minus of Dab divided by P minus Pa into P into dPa dr, that is Na here, into 4 pi r square is equal to small n. So, minus of Dab dPa, this we can write it as 4 pi into Dab into P dPa divided by P minus Pa equal to Na dr by r square. Now comes the integration. Now R equal to here Rs2, we go for infinity, right, because our objective is to calculate Na, small na, which remains constant throughout, right. The flux may be changing, but the molar flow rate remains constant. So, that will be up to infinity, and at the surface this Pa is equal to Pa sat, and far away Pa is equal to 0. So, here we have minus of 4 pi Dab into P. So, ln of P divided by P minus Pa sat, and that is equal to Na. Here we will have minus of 1 by r. So, infinity is 0, right. Infinity is 0. So, it will be give you simply Na divided by Rs. So, Na we can write as 4 pi into dAB into Rs into P ln of P divided by P minus Ps at. Now, it may be asked that how the naphthalene ball radius is changing in time if it is subjected to a pure diffusive sublimation. So, we can write here that minus of ddt, how the mole is depleting, it is 4/3 pi into Rs cube into rho s divided by m, and that must be is equal to 4 pi dAB into P into Rs ln of P minus Ps at. So, 4 pi and here this 4 pi cancels out. So, Rs square, right, Rs square into dRs dt, 3 and 3 will cancel out upon taking the derivative, into rho s by m is equal to dAB into P Rs ln of P divided by P minus Ps at. So, this Rs cancels here. So, if I now integrate, I will get this Rs 0 square initial radius at time t equal to 0 minus Rs square is equal to dAB into P into m divided by rho s into ln of P divided by P minus Ps at into time, right. So, again we get that it will decrease, naphthalene ball radius will start decreasing quadratically, right. So, this is the idea that how to incorporate the variable flux idea, variable flux concept where the area is variable, but the total molar flow rate remains constant. Let us take up another example, which is a diffusion through a tapered tube. Let us say it is an equimolar counter diffusion. So, here let us say it is diffusing through the tapered tube. Here Z is equal to 0, R is equal to R1, Z is equal to L, R is equal to R2, and at Z it has got a radius R, right. And we have a case of equimolar counter diffusion. So, you can write that Na into pi r square is equal to small na. So, an Na is equal to minus of dAB by RT into dPA dZ. If I use the basic equation that Na is equal to this Na plus Nb into Pa by P, capital P minus of dAB by RT into dPA dZ. So, Na plus Nb is simply giving you 0 because it is a counter diffusion flux. So, we have this Na. Now, R we can write this from R1 it is increasing, R1 plus R1 minus R2 divided by L into Z, right, and that is to be substituted here. So, Na is equal to minus of dAB by RT into dPA dZ into pi, and here we have R1 plus R2 minus R1 by L into Z's whole square, and that is equal to small na. So, obvious is that we have to integrate it with respect to this, and minus of dAB by RT it will be plus PA1 minus PA2. So, here it is 0.1 PA1 and here it is 0.2 that is PA2. So, the minus sign has been incorporated, it should be Pa2 minus Pa1 with a minus sign here, and we have these and pi will also be there. So, Na into dz divided by R1 plus R2 minus R1 divided by L into Z whole square, integral from Z is equal to 0 to Z is equal to L. So, if you integrate that, I am not doing this integration, I will get this expression for Na, right. I will get the expression for Na, and so this Na finally, if you integrate, it comes out to be pi into dAV by RT R1 R2 L into Pa1 minus Pa2, right. So, you see that if I have now a bulb which is fitted with this sort of tapered tube, and here we have Pa2 always 0, here we have Pa1 and the vessel volume is V1, this radius here is R1, here the radius is R2 and the length is L, right. So, minus of V1 by RT dPA1 dt will be the flow rate, and that we can write as pi into dAB by RT into R1 R2 by L into Pa1 minus 0, right. So, simply you integrate, considering that t equal to 0, Pa1 is equal to some Pa1 0, and at t equal to t, Pa1 equal to Pa1. So, from there you can get the dynamics, that how this Pa1 is changing with time, and definitely it will be an exponential decay with time, because this Pa1 will be coming here. If you integrate, there is a minus sign which switches to this, dt will be integrated to t, and you will get a kind of exponential decay. The exact mathematical form you can obtain upon integrating this with these two initial with this initial condition. So, diffusion so far we have discussed, see, it's called the molecular diffusion. What does it mean? We are saying throughout that this is molecular diffusion. So, whether there exist other types of diffusions as well? Definitely yes. So, molecular diffusion, so we have and this is a case of volume diffusion. Otherwise, we have this we are discussing volume diffusion. We can also have surface diffusion of molecules, but that here we are not discussing it. Other is called Knudsen diffusion. So, what is the difference? See, when a molecule, this gas or anything diffuses through a channel, right, these are gas molecules which are diffusing, right. So, if I consider F1, the frequency of collision with other molecules, and F2 is the frequency, definitely these are average frequencies, frequency of collision with channel wall. So, in case of molecular diffusion, F1 is much larger than F2, right. So, it will collide amongst themselves. However, if you go on narrowing down the channel, a point will come, say the channel radius is r, right. If we go on reducing the channel radius, there will be a shift of diffusion mechanism, right. This is very important. So, shift of diffusion mechanism means F2 will start getting comparable with F1, and there is a switch of regime. Definitely, it is not a sharp point. Initially, what will happen from the molecular diffusion, there will be a mixed regime where we will have both molecular diffusion and the other regime where the number or the frequency of collision is much higher with wall or comparable with wall, and that is called the Knudsen diffusion. Here F1 is much larger than F2, here F1 is comparable to F2, right. So, there will be intermediately a mixed regime like transition flow between laminar and turbulent flow. So, here we have a mixed regime where molecular diffusivity and Knudsen diffusivity both they contribute to the overall diffusivity of that molecule in that channel, and it actually happens in case of pores where there is a diffusion through pores of the solid, like in case of catalyst the gaseous reactants are diffusing in, right. And we will see in reaction engineering that actually the diffusivity we consider, it should be the effective diffusivity. Why effective diffusivity? Because it may be contributed by Knudsen as well as the molecular diffusivity. Generally, when the channel radius decreases below this around 50 nanometer or something, right. So, there we will have strong contribution, the contribution of Knudsen diffusivity also comes up. Okay. The Knudsen diffusivity Jk of A, it follows the same equation of Fick's law. However, the predictive equation of DAK is different from that of molecular diffusion. So, DAK or DA in general in case of molecular diffusion, we have seen that this Chapman-Enskog or Wilke-Chang predictive equation is valid, but here it will be something like this. It can be predicted from kinetic theory. Let us say it is Rp pore radius under root of T divided by M, where R is in centimeter. Right. Yes, 9700 Rp into under root of T divided by M. So, it is a typical Knudsen diffusion coefficient is in centimeter square per second, right. So, you see in case of molecular diffusion for gas, dA was proportional to T to the power 3 by 2 divided by P, whereas in case of liquid approximately we can say that dA B 0 at infinite dilution according to Wilke-Chang is proportional to T divided by mu. However, here the predictive equation is totally different, right, and it comes via kinetic theory. So, this is a new regime of diffusion which we often encounter in catalyst pores, and effective diffusion, we will see this, the roughly effective diffusion coefficient can be roughly predicted as 1 by dm molecular diffusion plus 1 by dk Knudsen diffusivity, right. But actually it has got some factor being multiplied by with it as epsilon and tau, where epsilon is a void fraction of that catalyst, there is a pore volume, and tau is the tortuosity of these pores. So, that is to be multiplied, but this term can be neglected and we can approximately write that this is in the order of 1 by dm plus 1 by dk, where dk and dm has got different expressions, their mechanisms are different, respective diffusion mechanisms are different. and different predictive expressions in relation to temperature and pressure. Okay. So, that is all about diffusion and molecular diffusion. Next, as I mentioned in the beginning of previous session, so we will now try to incorporate the effect of motion in the medium. That is, we are going from the diffusion, we are trying to solve now or to represent the convective flux, okay, or generally the flux what we observe in case of systems what we often deal in process industry, like in distillation, like absorption, like humidification, etc. Right. So, a topic will be here convective mass transfer and mass transfer coefficient. So, you see this diffusion itself, what we have seen that Na is either proportional to delta Pa or proportional, we can write it as delta Ya, or proportional to delta Ca, or we can also write it as proportional to delta Xa, right. So, mostly this delta Pa and delta Ya we use in case of gas. So, and here delta Ca this driving force and delta Xa the mole fraction based driving force for liquid, and here the mole fraction for gas that we use for liquid. These two we majorly use for liquid, this we can use for gases. So, everywhere in diffusion we are seeing that it is flux is proportional to the driving force, and driving force may be the partial pressure difference, maybe the mole fraction difference, maybe the concentration difference, all are reducible into other through this constitutive equation representing the relation between them. Okay. So, the fact is that this equation we will try to generalize through empiricity in case of convective transport. We had this equation in diffusion, right. Now, we will try to now extend this idea of diffusion to general transport equation which incorporates convection with diffusion or convection without diffusion, right. So, convective transport or mass transport equations, just like we have incorporated or introduced H in convective heat transport, and that the idea of H was derived from this diffusive transport by using film theory. Here also we will discuss this film theory as a potent and a very fundamental concept of this mass transfer. So, here thing is that first let us generalize this expression and with incorporation of certain empiricity. And what is empiricity? Empiricity is in terms of this coefficient. So, here we will write Kg into delta Pa, or we can write Ky into delta Ya, or we can write Kl into delta Ca, or it is Kx into delta Xa. So, these K's are basically what? They are mass transfer coefficients. And very often empirical. They cannot be determined via rigorous analysis except a few simplified cases, because whenever we have motion we have turbulence, and the motion itself to quantify, right, the turbulence to quantify, it is not so easy. We need this solution of averaged Navier-Stokes equation, Reynolds averaged Navier-Stokes equation. There are different models which can actually solve this nowadays, but it was not so easy when this theory was originally proposed. So, you see this in terms whenever we are changing the driving force, the units of this K also changes, right. So units of K also changes, like here it is mole per meter square per second, and here delta PA is in Pascal. So moles per meter square per second per Pascal, but it will be consistent if I write it in terms of concentration. So KL should have the unit of Na by Ca, delta Ca. So this is in mole per meter square second, here it is mole per meter cube. So giving you meter per second. So that is the baseline unit of mass transfer coefficient when we are expressing the driving force in terms of concentration difference. Okay. Now, this mass transfer coefficient, see, if we just link up the diffusive expressions, we can get the expressions of Kg, Ky, Kl and Kx. I am not doing it that, I am not actually describing that. So you can write the mass transfer coefficient, this mass flux expressions or molar flux expressions in case of pure diffusion, and can equate it to Kg into delta Pa or Ky into delta Ya in case of gas, and Kl into delta Ca and Kx into delta X in case of liquid, and from there you can get the expressions of Kg, Ky, Kl and Kx if we have pure diffusion. So this theory what we are trying to introduce here is equally valid for diffusion, but in diffusion we have the more fundamental phenomenological Fick's law, and from there we can directly integrate without actually introducing these empirical coefficients. However, in case of convective transport, we do not have a clear cut idea of the velocity field because of this complex turbulence phenomena, and as a consequence we have to go by empirical methodologies, right, or empirical approach rather, and that approach necessitates the incorporations of these mass transfer coefficients. So anyway, so typical magnitude wise, this gas phase also we can write in terms of concentration, this Kc, right. So here we can also write this is Kc into delta Ca for gas, and for gas phase. Here this delta X Ca for this is for liquid, L stands for liquid, this is also for liquid. So Kc, it is in the order of 10 to the power minus 2 meter per second, whereas delta, the film thickness, we will discuss this, but note that delta is in the order of 1 millimeter for gas, whereas for liquid Kl is 10 to the power minus 5 meter per second, and delta is in the order of 0.1 millimeter, right. This you note it down for liquid. This is approximate idea, right. So next, very similar to heat transfer, convective heat transfer, we have here, because we are incorporating empiricity to calculate these K values. So very similar to that, first we will introduce the different dimensionless groups very similar to convective heat transfer. So you see the Sherwood number we have described, which incorporates the heat transfer coefficient. So here, the Nusselt number we have described, and here we will just replace the Nusselt number by the equivalent mass transfer coefficient incorporating number dimensionless group, and that we refer as Sherwood number. So dimensionless numbers in mass transfer coefficient studies. So first one is Sherwood number. So Sherwood number, it is basically what? Convective mass flux divided by diffusive mass flux of A through non-diffusing or diffusive mass flux of A through the same or convective mass flux and diffusive mass flux of A for the same driving force. Right. And here the diffusive mass flux, whenever I am specifying diffusive mass flux of A for the same driving force through, I must specify the condition of B through a layer of non-diffusing B. Right, that is the definition of Sherwood number. So, if I use this Kg, so Kg into delta Pa, that is the convective mass flux. Now, diffusive will be dAb into P divided by RTL into ln of this PBL by, or rather we can write that delta Pa divided by PBM. So, Kg into L divided by dAb, Kg into L divided by dAb into RT into PBM divided by P. Right. So, you see that this Kg into RT we can incorporate as Kc into L divided by dAb into PBM by P. Right. And in case of a dilute solution, as Pa is much lower than Pb, so you can approximate it as Kc into L divided by dAb. So, that is the reduced form of Sherwood number expression, right. So, that is about the dependent variable group. Now, similar to Prandtl number, we introduce Smith number. Now, what was Prandtl number? Prandtl number was Cp mu by K, and that is equal to mu divided by rho and rho Cp divided by K. Okay. K divided by rho Cp. So, this is nu divided by alpha. So, that was momentum diffusivity by thermal diffusivity, right. So, it is momentum diffusivity divided by thermal diffusivity. So, very similarly we can introduce Smith number as momentum diffusivity is fundamental or baseline because it affects the convective transport, but not the heat transfer directly. So, nu divided by dAb. So, mu rho into dAb, that is the expression of Smith number, So, that is the momentum diffusivity divided by this molar diffusivity. Right. So, you see here, though it is not directly given in the handout, we must understand the concentration, the idea of concentration boundary layer, very similar to thermal boundary layer and also similar to hydrodynamic one. Let us say I have a solid plate from which material dissolves into the flowing stream. Let us say the plate is made of benzoic acid which dissolves in water, right, and we have a flow, a free stream uniform flow where the free stream velocity is u and its concentration is Ca infinity, whereas here at this interface the concentration of Cai, which is the solubility of benzoic acid in water. So, what will happen? Cai, let us say it is greater than Ca infinity. Now, this will be the growth, initial laminar growth of hydrodynamic boundary layer. Right? And hydrodynamic boundary layer, we know that we have discussed, this is the velocity profile, right. U is a function of x and y, and here at this delta we will have u equal to capital U, right. Now, similar to this velocity profile, we have a concentration profile, and the concentration profile will be like this. So, at a certain distance here, which is concentration boundary layer thickness delta C, here Ca is a function also of x and y, this is Cai and this much is Ca infinity, or let us write Ca naught, right. So, this much is the concentration boundary layer thickness, and if we go on joining this, I will get concentration boundary layer. Concentration boundary layer, right. So, you see that is very similar to thermal boundary layer. We can decide about whether the approximately whether the concentration boundary layer will be inside or outside or will be same as that of the hydrodynamic boundary layer based on the limiting value of Smith number equal to 1. So, if the Smith number is greater than 1, then basically mu is greater than nu is greater than dAB. What does it mean? The diffusivity, right, of momentum is higher than the mass diffusivity. So, it will penetrate more into the bulk of the liquid, and definitely we will have the delta greater than delta C. On the other hand, Smith number, if it is less than 1, then nu is less than dAB, we have delta less than delta C, right. So, that is the very basic idea of Smith number, very similar to Prandtl number. So, additionally we have the Reynolds number. So, what are the numbers? You see, we have Reynolds number, we have Smith number, we have Sherwood number, and very similar to heat transfer, we have here Stanton number, then Peclet number, Cold-Bond factor, and Grashof number, though it is valid for heat transfer, not exactly for mass transfer. Reynolds number, Smith number, and Sherwood number we have already discussed. Then Stanton number for mass transfer. Stanton number for mass transfer is Sherwood number divided by Reynolds number into Smith number. Right. So, basically it is if I write that Kc into L divided by dAB, and here rho into V into L divided by mu into mu divided by DAB, right. So, DAB cancels out, mu cancels out, and L also cancels out. So, it is Kc divided by rho into V. Okay. So, convective mass flux due to the mass flux. So, this is convective mass flux due to the mass flux or be divided by mass flux because of bulk flow. Right. So, it is multiplied by delta of Ca, here we multiply delta Ca, here L square, here L square. So, evidently the denominator gives you the mass flux because of the bulk flow. So, similar to the standard number, we have the Peclet number as this Reynolds number into Smith number for mass transfer. The Peclet number for mass transfer is Reynolds number into Smith number, and that gives you the flow due to bulk motion of that medium divided by diffusive flow across the layer of the same thickness. Just like rho into V into L divided by mu into mu divided by rho into DAB. So, you see that mu cancels out, rho cancels out. So, VL, whenever we have velocity, it is basically the bulk flow, and denominator is the diffusive transport. So, bulk transport rate divided by equivalent diffusive transport rate. Right. So, we have Peclet number, we have standard number, the meanings are basically very similar. We have this Cold-Bond factor for mass transfer as Sherwood number divided by Reynolds number into Smith number to the power here we can write directly the Stanton number into Smith number to the power 2/3. Right. So, and the correlations, just like laminar flow through a circular tube, we have discussed already in heat transfer, the same correlation will be valid here. The laminar flow through the circular tube first laminar and second turbulent. Here it will be the Sherwood number is equal to 1.86 into Reynolds number into Smith number into D by L to the power 1/3, right, 1.62, 1.62, right. Turbulent, that Sherwood number is equal to 0.023 into Reynolds number to the power 0.8, Smith number to the power 1/3, right. And it has got a validity range, like this is applicable for Reynolds number less than 2100, the second one is greater than 4000 and less than 60,000, or with Smith number less than 3000 greater than 0.6. Similarly, for boundary layer we can also express the same relation, and definitely there are other correlations which are all empiricals, and that has been derived from these experiments, right, and through dimensional analysis and repeated experiments in different systems. So, we will go on discussing this throughout the entire the subject of mass transfer, but what we have to note that these are simply outcomes of experiment, right. The numbers are defined, the physical significance of number we have studied, but in terms of that these numbers we have documented the empiricity of different equipments, different systems, and these are all system specific. Okay. So, next we have to go for these theories of mass transfer. But in the theories, before we go to the theory, just like we had this, see, tau yx we have written as mu into du dy, right, for fluid flow. whereas tau Ix turbulent we have written as mu into du bar dy minus rho u prime v prime average, right. So, this is the typical Reynolds stress. So, this we can write as mu plus Em eddy viscosity into du bar dy, where Em into du bar dy is equal to minus of rho u prime v prime average, and that is the analysis we have shown in fluid mechanics. Now, in molecular diffusion we are writing that J is equal to minus of dAb into dCA dZ. So, definitely when it comes to this turbulent motion we can write this Ed, this is a notation wise representation where Ed is the eddy diffusivity. And similar to this eddy viscosity, right, similar to eddy viscosity, eddy diffusivity of momentum, it is not only a property of that fluid, it depends on that flow, right. And eddy viscosity close to that interface actually it 0, because close to the interface we have a very low degree of turbulence. So, turbulence, the turbulence intensity as it drops, the eddy viscosity also drops, because this u prime v prime average is an indicator of this turbulence strength, right. So, Ed decreases close to the interface, and in general this is a correlation which we are trying to forcibly fit that Fick's law, just like here we are trying to forcibly fit the Newton's law of viscosity. So, that is the idea of turbulent eddy diffusivity. So, next we will go for theories of mass transfer. Now, first question, a very conceptual and fundamental question that we would like to first answer this question. It is that in heat transfer we are using only one theory, and that is a film theory, right. And from the film theory we introduced formally the idea of heat transfer or effective film heat transfer coefficient. Actually, the total name is not the heat transfer coefficient, we call it in short, the name is effective film heat transfer coefficient, right. So, it is coming out from the idea of film theory, but we do not have any other theories in heat transfer, generally it is not a baseline one, right. However, in mass transfer we have different 4 theories we are going to study. First one is film theory, the elementary one. The second one is penetration theory, the third one is surface renewal theory, and fourth one is the boundary layer theory. So, why there are so many theories in mass transfer where we are having only one in heat transfer? The thing is, if I see the interface mass transfer concentration profile, you see that okay, let's draw the heat transfer temperature profile. The temperature profile, let us say it is from the gas to liquid, gas is hot or the liquid is cold here. So, there is a temperature profile, right. So, it is continuous, okay, and on the both side of the interface it will have the same temperature. However, in case of mass transfer, if I plot the concentration, there is a discontinuity at the interface, because we have an equilibrium which comes out from thermodynamics as m into xi. Yi, which is the simplest equation, definitely we should write in general that this is a function of xi, right. So, there is a functional relation, they are not same. So, this process makes the entire mass transfer much more complicated than the heat transfer across the interface. Here the rate of heat transfer and here the rate of heat transfer same, but here also the rate of mass transfer and the rate of mass transfer will be same. We will maybe discussing in the after 1 or 2 sessions this interface mass transfer and the respective phenomena, but we have to understand that because of this discontinuity the things gets complicated, right. And only one baseline film theory may not be sufficient to understand the entire picture. So, that is why we, in order to grasp this complexity of mass transfer processes, we have multiple theories with multiple outlook and opinions, okay. starting from the baseline film theory and going up to the sophisticated this surface renewal or more elaborate boundary layer theory. So, here in the next session we will be going to discussing this theories of mass transfer, 4 theories of mass transfer, and these theories of mass transfer will actually will lead you to the idea that what is a physical picture, right? Physically how this mass transfer across the interface is happening, and from there we will actually close up this chapter and go for this gas liquid contactor device and the details of the different other equipments throughout this discussion regarding the subject. Thank you.